Hello, everybody, and good morning. It's honored to be here to present about some of my research going on in my PhD at Korea Institute of Energy Research. Okay. So it's honored to be here to present my some of the research topic of my PhD going on at Korea Institute of Energy Research. The topic which I am going to talk about is plastic upcycling through the solvothermal process to convert into carbon and oil production. So as everyone is familiar that due to the population increase as well as the requirements, the plastic uh, requirement of the world is increasing, and due to this reason, the most of the plastic, around 90%, is actually going into the waste. So here is the data showing about the global plastic production, which is reached to 400 million metric tons till 2022, which is global plastic production. And it is expected to reach to 600 million metric tons in 2050. And if we look at the different recycling strategies which are going on in the world to process and utilize the waste plastic, is only 9% of the total waste generation is recycled, and then around 19% is incinerated to produce heat, and other is going in the form of litter and landfills, and which is just throw away to the atmosphere. So talking about the different recycling percentage of the total production of the plastic, South Korea and Germany and other European countries like Denmark, Norway, and Switzerland are actually leading in the plastic recycling. And they are, for example, South Korea is recycling 61% of the total plastic generation they are producing. And other countries like Germany is the second highest, and they recycle 48% of the total production, uh, uh, plastic production in their country. So as I mentioned, that most of the plastic is actually going into the atmosphere, and in the presence of the atmospheric heat, it is decomposed into, and it is converted into microplastics, and creates a lot of problems for the aquatic life as well as environment and humans. For example, if it is thrown away to the sea, it will be very dangerous for the sea animals, and obviously most of the sea animals will be, not most of the animals, like if sea animals are taken this plastic waste, it will be problem for not only for their life but also for the humans, because obviously the sea animals are actually consumed by humans as well. So talking about the different recycling strategies which are being used at the moment, including mechanical waste, biological waste, as well as thermochemical waste. So mechanical recycling of plastic is just the plastic and then melting it and convert into other value-added products. And one of the most effective ways, which is going to be emerging in future, is thermochemical process to convert this waste plastic into kind of oil or other value-added products using the thermochemical process, which are mainly four, including gasification, pyrolysis, cracking, and liquefaction. So this slide compares the three different processes of thermochemical recycling of waste plastic, including liquefaction, pyrolysis, and gasification. Talking about the liquefaction, it is mainly performed in the range of 200 to 400 degrees in the high pressure environment to convert into oil, as well as producing other products like gases and solids. However, the energy efficiency of the liquefaction process is comparably higher as compared to pyrolysis and gasification, which is around 60 to 80%. So mainly liquefaction can lead to more oil production, which could be used as an alternative fuel, by upgrading it could be used as a marine fuel or sustainable aviation fuel. So this is the conventional way of at the moment going on in terms of waste plastic pyrolysis to convert into oil. And mostly at the commercial level, waste plastic is actually pyrolyzed to produce oil, gases, and char. However, this char, at the moment, the efficiency of oil is very low, which is around 20 to 30%. And mainly it is the carbon and hydrogen, which are important elements of, which are very important for the fuel and its properties, are going into the waste in the form of char. However, in our strategy, we have taken this char and further liquefied this char to further convert into oil, which could be heated further in the form of carbonization to produce solid carbon. And this solid carbon is further activated to improve its properties to utilize for various applications. For example, activated carbon could be used because it is, if the purity of carbon is very high, it could be used in water treatment applications, sensors, solar cells, energy storage, electrochemical devices, and so on. Similarly, the oil which could be produced from waste plastic could be utilized for various applications. As I mentioned, if it is heat up, it could lead to the carbon material production. Similarly, if oil is distilled, it can lead to various chemical productions. And if it is upgraded, it can be used as a marine fuel or jet fuel. And after separation, it can be used as heavy oil as well. So if and further, it could be converted into hydrogen through the process of steam reforming. So this is the waste plastic residue which we have used in our study. And here is the approximate analysis data of showing volatile matter, ash, and fixed carbon composition, the percentage in our waste plastic feedstock, which is used for oil and carbon production. So here is the process flow for methodology. And here the first is the plastic is dried and then perform the liquefaction. And after that, oil and char are separated using centrifugation, and oil layer is separated using filtration, and then solvent is recovered through the distillation process. After this recovery, one product is oil, and further in the route one, it is carbonized to produce carbon. In route 2, it is just separated out from the solvent and it is used as the oil. So here we have tested different experimental condition by varying the reaction at this liquefaction temperature from 150 to 300, as well as the time from 15 to 45 minutes, as well as the carbon production from 3 to 9 hours. So here is the effect of temperature on the carbon recovery from the plastic. And it was performed at 250 and 300. And here we can see that in the carbon recovery was 25.2% at 250, which was decreased to 23.4% by increasing the time. And then in the residue carbon, because there were three products, char, gas, and oil, here in the residue, the carbon left over was only 6.7% based on the approximate analysis data. So here is the effect of time, studying 15 minutes, 30 minutes, and 45 minutes on the recovery of this carbon. And here we can see the carbon recovery was 34.8% after 15 minutes. And similarly, by studying the like the long time, here we can see is from 3 to 9 hours, the maximum carbon recovery was after 5 hours, which was 30.5%. So these are the recovered carbon sample from the waste plastic. And here we can see that the carbon was successfully recovered from the waste plastic samples, plastic residue samples. So here is the summary of just waste plastic residue into the carbon. Here we can see that with the increase of the time, the recovery was decreased due to the decomposition of oil into the gaseous components which are removed from the system. So these are the TEM image of recovered carbon, and here we can see that there are two forms of carbon present, amorphous and graphitic carbon, and there are no impurities detected in the TEM images of the recovered carbon, which shows that the carbon was very highly pure and it could be used for various applications which I mentioned earlier. So here is the comparison of our waste plastic residue into carbon sample with other studies by comparing the properties of this recovered carbon with other researchers like waste tires, PET, and coffee cups. And here, the main important composition which really matters for the effective use of plastic is fixed carbon and ash content. Here we can see the fixed carbon is very high compared to other studies which were 95.3%, which means that it could be used for various applications because of low ash content in our samples. So another route for this research was to convert waste plastic into oil, and here we can see the effect of temperature on oil production and the overall conversion of waste plastic residue into the oil. And here we can see by increasing the temperature, the oil production from waste plastic residue was increased, and 275 degrees, the maximum conversion and oil percentages were observed, like 43.32% oil yield and 66% of overall conversion. Similarly, this slide shows about the effect of time on the yields of oil, gases, and char, as well as the overall conversion. And again, at 45 minutes time and the optimum temperature of 275, the maximum oil yield was 45.37%. So here is the TGA analysis of oils performed to check the boiling ranges of the compounds present in our samples. And here we can see that light oil compounds were dominating, and which means that if it is used for oil, it would be good to burn the oil in the engines easily to get heat to run the engines. So similarly, here is the higher heating value data of the oils recovered as well as the elemental composition. As we know that higher H2C ratio of any fuel is very important to get the high fuel efficiency, and here we can see is around 2.1%, which is very close to the conventional gasoline, as well as its higher heating values, which were in the range of 45 to 46 megajoules per kg, which is very close to the conventional gasoline, which is currently used as a fuel. So here is the GC-MS data of the oil, showing the hydrocarbons and paraffins were dominating in the samples, and aromatics were very low, which means that there is not much upgrading needed to be used as a conventional fuel, as a commercial fuel. So talking about the conversion and the recommendation, the carbon was successfully recovered from the waste plastic residue as well as oil, getting 42 to 45% of the the oil yield, and high carbon recovery of 34.8% after 15 minutes, and the highest oil recovery at 275 degrees. So in the further, we are going to actually test various different solvents to improve the carbon recovery efficiency as well as oil yield, and to optimize the conditions of activated carbon to use in the area of, particularly in the catalysis, because very high BET surface areas are required. So it is important to improve the carbon purity as well as the overall properties to use for various applications. And then in order to convert the aromatics and improve the properties to use as aviation fuel or marine fuel upgradation, we are going to work on the upgradation of this oil for aviation fuel applications. So that's all from me. Thank you very much. Any questions?